Okay. So what we have is charge Q1 at X1, Y1, Q2 at X2, Y2, and a test charge Q test at X1. Let's see how much work it takes to move Q test from infinity to XY. Well, you have to do an interval. And what I'm recommending is ignore Q2. Or if you'd rather ignore Q1, that's okay. Ignore Q2 and bring this thing in along a straight line. It goes through X1, Y1, and XY. Okay. And if you do that, you call this straight line RX. Okay. Figure out where you want to put the origin. And integrate the force along that axis. And well, having done this, take an interval. Your R-axis. And you calculate the force. Okay. Times the length of the interval. You have an interval. Delta R with a sample point. R star. Calculate the force at R star and multiply that by your delta R. Then get your signs right. You're to be able to easily get the force. Okay. Another thing I would do is I'd put the origin of my R axis here. And then figure out what the R coordinate ought to be here. So you know what the limits are in your interval. Gonna go from infinity, whatever the R coordinate is. Okay. And you're moving this way. So see much of that you can sort out in just a couple of minutes. See if you can at least tell me what the expression would be for the force at this point. And then hopefully the force times this. Okay. Okay. Y'all did pretty well. You know what the integral is going to be, but nobody's told me what happens in this interval. And you have to get used to telling me what happens in your typical interval, because an integral is something you get from a partition of an axis or a region. Multivariable calculus, presume we're going to be partitioning plane and solid regions. Okay, and you have to get the idea of partition in mind, you know, for that. But you also need it for physics, because that's where you really end up applying. Let me come over here and say, okay, here's my R axis. Here's charge Q1 at R equals 0. And here's my charge Q test at R equals 1. Well, how far is it from here to here? That's how far. Pythagorean theorem tells you how far. Now you're not wanting to use X and Y because we're on an R axis, right? But the information is given to you in terms of X and Y. You're going to have to use them. You're not going to integrate with respect to X. You're not going to integrate with respect to Y. You're going to integrate with respect to R. But you got to have an expression for this distance in terms of the information we gave you. Make sense? Okay, so even there's natural hesitation. Um. So R equals. So I don't want to take up all my room there, and I should have left myself a little more. Okay. That's at this point. Now we take this interval. Delta R. We've got some coordinate R star here, somewhere between infinity and square root of x minus x1 squared plus y minus y1 squared. Okay. Let's just look at that interval. And I'm going to write the interval horizontally right now because it's a little easier to manage. But we understand we've just taken this interval here. Now it's down here in the direction. Doesn't make any difference. I didn't specify a direction. I said you got these coordinates. This line might even be horizontal. Might be vertical, probably some other angle. In general, it's just whatever angle. Okay, well, here it is. So we got delta R. And we got R equals R star. How much work? But you need to know find work. Force, distance. Force displacement. It's all going to be along the same line. So there's a force here. So imagine that Q test is right here. Force on Q test is, and everybody has this. Everybody wrote an integral. It was the right integral, but you didn't develop the integral. You just wrote it down. And I'm not convinced that you know how to develop the integral. And it's becoming critical that you be able to do that. Okay, so that's why we keep emphasizing this. Force is this, and it's directed I'll say in the positive R direction, but not really. Because Q test might be negative. If it's in the positive direction, and Q1 and Q test have the same sign, then it is directed away from R equals 0. It's directed toward infinity. Okay, so that's a positive R direction. If these have negative opposite signs, you get a negative here, right? Well, what's a negative force in this direction? It's in this direction. Okay, negative sign reverses the force. So instead of saying in the positive R direction, we're going to use this R hat that you see in your text, the unit vector in the R direction. Okay, so I'm going to replace my in the positive R direction. And I'm gonna say, okay. Then this is ought to be R star. The R star ought to. Let me write it. Essentially, well, put that star where it belongs. Let me try again. The R star vector with a hat indicating it's a unit vector. Well, to complete that picture then. Here's your R star vector, the origin out to this point. Okay. And we unitize this by dividing by its magnitude. So now we have the R star hat vector. And I'll write it out explicitly. I'll get a little flutter. I've written it kind of small, but it's this is R star divided by its magnitude. Unit vector. Okay, so there's my R star hat. There I have it. And the work. This part. Well, my direction is from infinity to Q test. I asked for the work from infinity to Q test. So my delta R is actually going to have a direction. Delta R is in this direction because we're moving toward position of Q test. So what's expression for the work? Go ahead and write it down. Again, most of you know what the integral should be up to a sign. You're going to worry about whether it's a plus or minus sign and whether we're talking about the work done on the charge or the work done by the force. Okay. So we've got to make that distinction. Turns out that the work then put our delta R interval delta R star, which is a magnitude of this vector, is the distance from here to there, equals the same expression I wrote down here. This is the force exerted on the charge. So F of R star times delta R. Gonna be negative. Look at this. Not equal, another. Oh. From where to where? Well, I said from infinity to this position. So the interval would be from infinity to this square root, right? That's small. Your x minus f1 squared, x1 minus y1 squared. Under the bracket. Now let's think about what this is. Is that the work done in order to move the charge to this point? Or is it the work done by the force on the charge? In other words, charge is moving this way, the force is in this direction. Okay. So then this integral would be the work done on the by the force. Okay, which is negative if you're moving from infinity to whatever distance. Okay. The work you got to do to move that thing is in the direction of motion. Okay. Why didn't have a sign from? This is the work done by the force F1. The work to move the thing from here to here is equal and opposite to that. There might have been some problem here. We'll work it out. Okay, so anyhow, if you integrate this, you're going to get a negative in here. Okay, which will match up with this negative. Your reciprocal R at infinity is going to give you 0. Your reciprocal R here is going to give you a positive result. So if Q test and Q1 have the same sign, you're integrating the negative of a positive quantity. Okay. But you're going to end up with a positive result because the negative you get when you do the integral. Okay. So these signs are correct. Okay, well, anyhow, then, following this reasoning, Let's see. So that's integral. I've got a delta W, the sum of the delta W is this. So the work. Actually, I got it turned around on the slides. But I didn't quite correct. The work delta W is again this integral from infinity to that square root of do the details, and you're going to get KQ test Q1 over R. Over square root of X minus X1 squared. I'm going to call that negative KQ test Q1 over R1. I'm going to call this distance R1. All right. And then, of course, I've got Q2 somewhere. Yeah. Okay. So that R1. And R2. Same expression, but X to the next one. The work is that's not right. Okay. Work per unit of test charge is KQ1 over R1 plus KQ2 over R2. Okay. No, I have too many negatives in this. I have a negative there. Shouldn't have a negative there. Shouldn't have a negative there. Should have a negative here. Work by the field is equal and opposite to the work done but on the charge. Okay. This field does 100 joules of work on the charge as it approaches. That means I've got to push the charge. I've got to do negative work to do it. Okay. This field's pulling the charge in. then I've got to hold it back. Which means I'm doing. Okay. I mean, do that. Hold it back. Well, okay. Well, that's the intuitive thing. Now, the bottom line is. This expression is the electric potential of this system, because it's how much work we need to create the system. Right? So, details of the integral aside, and you've got to be able to work out these details. This distance is R1, this distance is R2. Well, the potential energy. AQ1 over R1 plus AQ2 over R2. Now, what's our definition of potential energy? It's equal and opposite to the work done by the field, which is work you got to do to assemble it. Now you have the work of a point charge. I mean, the potential at a distance R from a point charge is KQ over R. Okay, you got a bunch of point charges, you got to integrate. You have to integrate over a ring charge or a sphere charge or whatever. Okay. If the potential energy equals C, what's the region of constant potential energy? Well, AQ1 over R1 plus AQ2 over R2 equals C. If you solve this equation in coordinates, you're going to get a curve. 2 dimensions. If you go to 3 dimensions, well, you just rotate that curve in every possible direction and you get a surface. This is an equipotential surface. Equipotential surface for point charge. Let's say you got a charge for the Q. Well, the potential is the same. Okay, so let's say the potential here. Where else is the potential? Okay, so potential is C here. The potential at any point K Q over R, your book writes it as 1/4 pi epsilon naught Q over R. And again, there are places where K is preferably epsilon naught, just more convenient, equivalent, okay? And there are places where epsilon naught is going to be more convenient to take. I'm going to get capacity. Right now, I'm going to stick with K because it's shorter and I don't have to write as much. Takes up less space on the board, takes up a little less time. Okay, so what's R? R is a distance from here to here. Okay. Now, where else would the potential be the same as it is at that point? Let's take Q over R, right? Yes, it's all points at distance R. So we can write, we can sketch points, all distance R, let me reference points around here, so I get a reasonable circular picture. Okay. And it's actually a sphere. Can't draw a sphere on the board. I mean, okay, same potential, any distance R. The potential is the same in every sphere at the given point. This is a given point. Just draw a sphere, but dark cube, and there you have it. Okay. Where then would be would the potential be two? Okay, we got a pretty quick answer on that. The potential is 2C. And you have 1/2 R. Okay, because the potential is inversely proportional to R. You double R, you get half the potential. You want twice the potential, you cut R in half. So that's just basic proportionality. Half R. Words written all over the pages of proportionality. So we go to 1/2 R. So here's the equipotential surface. Equal C. B is our symbol for potential. And it's voltage. There are measured volts. And here's the potential surface. Or B equals 2C. In other words, it takes twice as much energy. Bring a charge from infinity to here. As it does to bring it from infinity to here. That's not much distance compared to an infinite distance. But of course, the force falls off in an inverse square proportionality. Okay. So you go much beyond this and you get pretty much almost no charge, almost no force, and almost no work. Could say more, but I'll leave it at that. So if we want half the potential, we just got to go twice this far. Okay. If we want half of that, well, we got twice this far. We keep taking half, whatever the potential is here, pretty soon you don't have much potential. You do that 10 times, double your distance here 10 times. And you're going to be down to less than 1,000th of the potential. Because every time you double your distance, you have your force. You cut it in half 10 times, you get 1,024th. 2 to the 10th is 1,024. Okay. So you want to kind of think about that. So your potential surfaces, you'd be using the same increment of potential. So let's say you have potential 2C, cut that in half, you get potential C. Okay. Well, that's what I said. Now, if you go from 2C to C to 0, equal increments. 2C, C, 0, well, 0 is not there at infinity. Can't even draw the surface. Now, if you want 4C, you go in twice as close. And you go over 2C, right? And then if you go in twice as close, you'll be doubling that, you get 8C and 16C. So you cut this distance in half 1,024 times, you get about 1,000, about 1,000 times potential. That takes 1,000 times the energy to move this in to a distance of 10 halvings. Of course, that's going to make this distance pretty small. The other thing that's obvious, you keep doing that without limit, and your limit as your distance here approaches 0 is infinite. Which of course you can tell just from the formula here, as r approaches 0, it's going to approach infinity. And well, that's the idea of equal potential. What would the equal potential surface look like for a uniform spherical charge distribution? Okay, a charge Q is the origin. Going to want to do this in XYZ coordinates for reasons that'll become apparent pretty quick. So you got XYZ here. Some point. And this distance, well, what's this distance? The square root of x squared plus y squared plus z squared. Okay, potential. A Q over R. Okay. Now your book gives you a formula. Finding potential, okay? Or for finding the electric field if you know the potential. You don't need that formula because what did we do yesterday? Find the gradient, right? Formula is the gradient. You look at the formula, you see the gradient if you work with the gradient. If you haven't, you're gonna be working with it the next day or two because it's assigned. Okay? They're already looking at it, but I know how the world really is, doesn't always happen. Okay, so equals what now? Now, real quick. Okay, can't call you by name because we're on camera. I'm just gonna be impolite and point. You do the partial D with respect to X, you do the partial D with respect to Y, and whoever's left over do the one with Z. Okay, and that would be. Okay, well, just as an example. You know, work out the example in detail, but hopefully the reminder is all you need. First of all, KQ's constant, so it's KQ times partial with respect to X. This, and there are several ways you could annotate this. I'm going to put it in this form. Okay, so you don't have to use the quotient rule. It's usually my preference, but the quotient rule is not that difficult either. You know, your F prime G is going to be 0, your FG prime is going to be 2x. And your denominator is going to increase its power. Okay, and then you have a coefficient due to the square root. All that goes together. So you can do it. And I'll do it as well. First of all, the derivative of the 1/2 power is a -3/2 power. But of course, you have a 1/2 power times power 1 less. That's just your basic power function rule. But you have a chain rule because you have an inner function here, the x squared plus y squared plus c squared. You gotta multiply that by 2x, the derivative of this inner function with respect to x. That's just x over 3x. Okay. And if you do the y and the z, you find that the gradient is well, you're going to have for the partial b with respect to x, you're going to have an xi in the numerator, and you're going to have the square of 3/2 power in the denominator. Okay. This one, well, you're going to get a y. all this times AQ. X squared plus Y squared plus Z squared is R squared, isn't it? That's R squared to the 3/2, that's R cubed. Okay. The magnitude of this is R. So that's equal, and you probably have to work that out at some point in the board. AQ of R squared. Well, what's the electric field of a point charge at distance R? AQ over R squared. Okay, but it's times now a vector. And it's I'm gonna write it out. You probably need to work it out. I just don't want to spend the time on it. I don't think that helps with myself state. Okay. R hat is a unit vector. What would the unit vector be? Well, this is like R2. Too much to say. Okay, you just work it out. Okay, the unit vector is going to be just 1 over the square root of 3 times I plus j plus k. Sorry, no. Yeah, you're gonna still have the xi plus yk plus z thing. Yeah. Got other things we need to talk about, but that's the idea, okay? So the gradient works out. Now you're gonna have problems with gradient, multi-level calculus, and have problems using the gradient here, even though they call it the gradient. It just gives you the formula. Right there is the formula. Okay. So you know it's the gradient, you don't have to use the fact that it's a gradient. But it is the direction of this is radial. Because xi plus yj plus zk is a radial vector. It's a vector from here to here. Okay. Thing is radial. It's the direction of greatest change in the electric field. If you move along this radial line, and I think, you know, there's a negative here. That should be negative x. It'll be the negative of x. But it started the same. All of a sudden wasn't consistent, okay? The direction of greatest change is radial, but it's toward the origin. Well, where does the electric field change most rapidly? When you're approaching the charge. So this vector is in the direction toward the charge. That's the direction of greatest increase. Its magnitude is magnitude of the electric field. So you can work all that out. Those for the details. You know, then you can find AE is a great interview. Gonna go back to the Earth and the Moon. For an analogy that's maybe easier to understand, but maybe not. Let's see. This is the Earth. And this is the Moon. Yeah. I have a satellite here. Well, if the moon isn't there. The satellite would follow a circular orbit. Okay. It stays in the potential surface. That makes sense. Because equal potential surface for the same reason. Yeah, I mean, if this was a charge. The potential surface of everything is equal radius. You remember anything about gravitation? You know, it's a circular orbit, it's going to follow a circle. And the circle would be equal potential with the gravitational field. The gravitational field has exactly the same mathematical form as an electric field. And especially easy to understand if you just have a single mass. And now if you got another mass, now we're going to put the moon here. What path is this thing going to take? If it starts out on this circle with some velocity, the velocity to keep it in the circle, and when you pull it out. Have two potential surfaces are gonna, I don't know. Something like this. Okay. And they're gonna warp. And you can work out the mathematical form. Is quarter R between these. So that's kind of an analogy. But now if I have a plus Q and negative Q. Well, we saw this potential surface. Here it would be on the perpendicular bisector. So we can follow any path between Q and negative Q for free. Okay. Now, a gravitational equipotential surface is never going to look like this. Because you don't have opposite gravitational forces. Mass attracts mass. It never repels. Okay. What I'm going to put is, if I put a charge here, it can move anywhere on this surface as though it's spinning through better. Analogous to the fact that a satellite can stay in a circular orbit with no expenditure of energy. In the ideal case. There are tidal forces and stuff like that, but that's going to do influence things. Okay. Now, if I want to move closer here. What's like potential surface look like? Well, if it was just this charge, the potential surface would be here. If there's this charge as well. So if I try to move on a circle, with this one, you're going to get a net force. And net force, let's say at this point, you have a big force toward this and a little force toward this. Okay. Well, that's going to distort my potential surface. And I'm going to pull it out this way a little bit. Here. It's going to make it lopsided over here. At this point, you get the same net force. I can't be as close to negative Q as I was here. Because I'm further from plus Q. I'm getting less force from this guy. If I get the same force from negative Q, I've got a lesser net force, okay? So we have to do this. So in this field, we can follow this path. Okay, and similarly over here. The shape is going to be symmetric. Negative through one. That's the kind of stuff we're gonna get. That's the picture. You can look at. Okay, the point about eight potential surfaces, you want to really lock in, is you move on them for no expenditure better. That's really what it comes down to. Okay, well, we're out of time. Hopefully I've given you enough images and stuff that you can work reasonably through the assignment. I think the assignment, for some reason, is due on the 4th. Today's the 1st, isn't it? So the 4th would be like Saturday. Should be Sunday. So I'll try to make it a point to modify that. Also, if you're having trouble with Gauss's law and visualizing in 3 dimensions, I've got some problems. And I'm trying to find time. I've got them written, I just got to debug them. So I'll be getting those out almost certainly tomorrow. Microphone. Go ahead, some questions. Okay, I haven't forgotten that. Okay. Let me stop.